Hello friends, welcome to my YouTube channel Maths and Stats Forum. My name is Doipan Datta and today I am going to discuss about some advanced level problem on Rolle's theorem. Now friends, previously I have discussed about some basic theory of the Rolle's theorem and also some very basic problems on Rolle's theorem. But in this session I am going to discuss about some advanced level and application based problem of Rolle's theorem, which will help you to get an idea that how to tackle this kind of problems on Rolle's theorem. Actually, this is a second session on real analysis and we will only keep in mind the real part of the equation and the real part of the roots. So, without wasting any more time, let's get started. See here friends, we are given this function f of x is equal to 4x to the power 5 plus x cube plus 7x minus 2, and we are asked to show that this function fx has exactly one real root. Now see this function, if you observe this function, it's a polynomial function and this function has the highest power of x is 5. That means it will have 5 roots, but we are asked to show that it has only one real root. That means the remaining 4 will be complex roots. But here I have told you that this is we are discussing about real part only, so we will only concentrate on the real thing, real roots. This is the equation. I am showing this is equal to f of x. Now if we put x is equal to 0, we get minus 2, and if we put x is equal to 1, we get this as 10. So it means that if we draw a function, if we map this function, it will be something like this. At this point it will be 0 and minus 2, and at this point it will be 1 and 10. So here I have, as we can see, that there will be a 0 between these 2 points, right? That is between x is equal to 0 and x is equal to 1, there will be at least one point at which this function will be equal to 0. And also the mean value theorem tells the same thing, that if this value, actually not mean value, the intermediate value theorem tells the same thing. Now according to the intermediate value theorem also, it also says that if a function is continuous within this closed interval ab, what is a 0 and what is b 1, and it is differentiable within this open interval ab, then there will be a value c which will be lesser than b and greater than a, such that f of a right. And if we make an analogy with this of this part with this graph, what we can say is that there will be at least one real root between this 0 and 1. For at least one real root, remember friends, please consider there will be at least one real root for this function between 0 and 1, and this is the main conclusion of intermediate value theorem. Now choose 2 points a and b in this function. Now suppose this function is polynomial, so this f of x is continuous within a and b. It is this fx is also differentiable within this, and suppose if you draw this above function like this, this is a and this is b, right? Then we can say that f of a is equal to f of b is equal to 0, right? Now see, are you getting any kind of similarity? Are you recalling anything from the previous session? Yes, this is the 3 conditions of Rolle's theorem. If these 3 conditions are getting satisfied, then this fx then actually there will be point C between this AB such that this f dash of C is equal to 0, right? And we just have to prove this, that it has only exactly one real root based on this part only. Now we have this Rolle's theorem in our hand, and we have to follow the concept, and we will get to reach our destination. If we differentiate this f of x now, so what we are getting is 20x4 plus 3x squared plus 7, right? We are getting this thing. Now friends, if we can try to put any real value of x at which this f of x will be 0. Remember, put any real value, not complex, but real value at which this f dash of x will be equal to 0. Try to put here. I am sure you will be trying, but you will fail, because see, whenever what will be the real value, whatever be the real value of this x in this equation, it will be never be equal to 0. Now friends, if you keep on trying, you will see that whatever root you get for any real value of x, this f dash of x will not be equal to 0. For any, remember, for any real value of x, this f dash of x will not be equal to 0. You can try and try, but you will fail. What you will see, the value of this f dash of x will always be greater than equal to 7, right? So if this is the ultimate conclusion, then what we can say, that Rolle's theorem is failing miserably here. Thus Rolle's theorem is also failing. So we will say that there are not at least two roots, but exactly one real root, because this is a polynomial function. And since the Rolle's theorem has failed, so we will say thus this f dash of x has exactly one real root, and thus hence it is proved, because we are asked to prove this part, that this f of x has exactly one real root. We assume that there are two real roots, but we failed. Why? Because Rolle's theorem was not applied for that part. That's why we have to conclude that it has exactly one real root, because it is a polynomial function, it is continuous, and at only one point of x it will be 0, and thus it is proved. So let's go to the next question. This question is also like the previous one, guys. I am explaining you so that it gets better for you to understand. These problems you need to practice a lot to get a hold on this real analysis. And mind you, and let me tell you guys, this is a very scoring part of this mathematics. For students of B.Tech, for students of B.Sc also, you will find it very scoring module of mathematics. See, this is the function we are given, and we are asked to find, actually we are asked to show that this function has exactly one real root. See, the approach will be same as the previous one. I will show you. I am just repeating the same thing so that it helps you to understand better. Now friends, this is what we are given, and see, this is a function. Suppose we say for x is equal to 0, what we are getting is 8, and for x is equal to minus 1, what we are getting is minus 1, minus 7, minus 25 plus 8. So for x is equal to 0 we are getting 8, for x is equal to minus 1 we are getting minus 25. So if we draw the curve of this function, if suppose we say this is minus 1 and minus 25, this point is minus 1 and minus 25, and suppose this point is 0 and 8. So the function will go like this. Suppose the function goes like this and the shape of function is like this. Actually, I don't know what is the shape, I am just taking a random shape curve, but the two things which is confirmed about this function is, since it is polynomial, it will be continuous and differentiable. These two things are confirmed about this function. Now, as we can see here, that there is at least one real root. See, here we are getting this function as 0, which means that there is at least one real root of this function. Now, as I have discussed in intermediate value theorem, that there will be a function c, there will be a value c between a and b. What is a? A is 0 and what is b? B is minus 1. I am sorry, a is minus 1 and b is 0. See, this is a value between minus 1 and 0, for which this f of c will be greater than this f of minus 1 and f of 0, right? So in other words, we can say from this intermediate value theorem, we can say that there will be at least one real root for this polynomial equation. Suppose we are taking the graph like this. This is 0 and at this point here the function is also 0, right? X is something, here is, let's say x is a, and here x say, here say x is a and here say x is b, right? Here, as I told you, that the function in this part was, and this is 0 and 8. So I am taking the previous details only, right? Now in this part only, see, in this part the function is continuous and differentiable, right? And see, at this part also, there and here, that is at f of a is equal to f of b, and both the values are 0. So we can say that Rolle's theorem can be applied here, right? Which means that there will be a point C within this a of b. Suppose at this point C, this is the point C, at which f dash of c is equal to 0, right? We can see that. So we are assuming this part, not assuming, we are saying that this part can be used to verify Rolle's theorem. What can be interpreted from this part? That it has two real roots. We can also say that it has at least two real roots, because if the function change, and if not the function change, I am drawing a graph randomly, but the graph may be like this also. So there will be, here there will be a root, here there will be a root, and here there will be a root. So at least two roots. So assuming at least two real roots, we are assuming that it has at least two real roots. Now it was continuous within interval AB, it was differentiable within this open interval AB, and as I have showed you before, f of a is equal to f of b, which is equal to 0. Then there will be a point C which will be within this closed interval AB, such that f dash of c is equal to 0. Now to prove this, we have to differentiate this function, right? So now we are differentiating it. See, f dash of x will give us 3x square minus 7x plus 25. Now to verify the Rolle's theorem, we have to equate this to 0. So we are equating this to 0. When we equate this to 0, what we see that we will be getting the value of x, but the value of x will not be real. You can calculate yourself, but the value of x will not be real. Here we will get the value of x will be complex. It is in the form of a plus ib. See, equating this part to 0, what we get that the x will be equal to this thing. So it's a complex number. But what I told that we need to deal with the real numbers. So the Rolle's theorem is getting violated. It is getting contradictory. That what we said that there will be at least 2 real roots, right? But if there are at least 2 real roots, then this part will be real. It will not be a complex part. This value of x will be a real number, then not a complex number. It means that the assumption what we are getting is contradictory with this statement. So we can say that there are not at least 2 roots, but exactly 1 real root. As I have shown you in the graph, there will be exactly 1 real root, which we also partially concluded from the intermediate value theorem. What intermediate value theorem said? That there will be at least 1 real root. But from all this part, we will say that there is exactly 1 real root, because if there are more than real roots, with this Rolle's theorem will be verified, and this x will be a real value, not a complex value. Now see this problem, guys. Here we have said that alpha 0, alpha 1, alpha 2 all are up to alpha n, all are real number, and alpha 0 by n plus 1 plus alpha 1 by n up till alpha n is equal to 0. We are asked to show that there is at least one value of x which belongs to 0, 1, such that this alpha 0 into x to the power n plus alpha 1 into x to the power n plus 1 till alpha n will be equal to 0, right? We have see the problem very carefully. If you recall, please note it down. It's a very important problem and very interesting problem. So we will solve it part by part, and let's go. See, we are given this part, right? Now see friends, we are given this one, and we are assuming a function phi x which is equal to this lambda 0 by n plus 1 into x to the power n plus 1 plus lambda 1 n into x to the power n up till lambda n into x, right? We are assuming this thing. Now what we are told that we have to prove that for every x which belongs to 0, 1, this lambda 0 x to the power n plus lambda 1 x to the power n plus 1 will be equal to 0, right? We are given this thing. Now friends, observe carefully. This function is a polynomial function, right? This function is a polynomial function, so it will be continuous within the closed interval 0 and 1. This function will be continuous within the closed interval 0 and 1, and it will also be differentiable within this open interval 0 and 1. And there will be a point x, and there will be 2 points A and B for which this now see friends, this is a polynomial function, right? It's a polynomial function. What it means? That this function will be continuous within this interval, closed interval 0 and a, and it will also be differentiable within the open interval 0 and 1. So we can say this continuous within this closed interval 0, 1 and differentiable within the open interval within the open interval 0, 1. But to apply Rolle's theorem, another condition must be satisfied, that this phi of 0 is equal to phi of 1, right? This thing must also be satisfied, so to apply the Rolle's theorem. Now observe something. If we put 1 in place of x, what we get? Phi of 1. Calculate phi of 1. What we get? If you calculate phi of 1, that is, if we put a 1 in place of x, you will get lambda 0 by n plus 1 plus alpha 1 by n plus alpha 2 by n minus 2. This will go on. And do you think, are you getting something similar to like this? See, this equation, this expression has already been given here, and we are told that this expression is equal to 0. So this phi 1 is equal to 0. Again, if phi of 0, what does this mean? That we have to put 0 in place of x. So if we put 0 everywhere, so the whole thing will get 0. So this one is equal to phi of 0. So the third condition of Rolle's theorem is also satisfied. The third condition of Rolle's theorem is also satisfied, and thus the three conditions are satisfied. So we can say that there will be a value of x within 0 and 1 for which this phi of x function will be differentiable, and at that point f dash of x will be, phi dash of x will be 0, right? We can do this by Rolle's theorem. The three conditions of Rolle's theorem are satisfied. Now let's differentiate this. Now if we differentiate this, what we get? Lambda x to the power n, lambda 0 x to the power n. Why? Because see, here is n plus 1, here is n plus 1, it will cancel out. Then lambda 1 x to the power n up to lambda of n. We will get this thing, right? Now according to Rolle's theorem, what we are told, that there will be a value of x within this 0 and 1 such that this expression, we have said that this expression lambda 0 x to the power n plus lambda 1 x to the power n minus 1 will be equal to 0. So this is the function, and this function will satisfy Rolle's theorem, right? And thus we can, from this part we can conclude this part, that is, this thing is equal to 0. And we are asked to find out, if we have followed the question, I have already written you, since this question was a little bit big to write it down, so we are asked to show that this part will be equal to 0, right? And since phi dash of x is this one, so according to Rolle's theorem, this part will be equal to 0 for x which will lie within 0 and 1. Thus it is proved. So that's all from my friends for today. If you like my video, please like and comment whatever you think about the video, and please don't forget to subscribe my channel. If you have any doubt related to this Rolle's theorem, please don't hesitate to comment in the comment box. Thank you.